Calculating a customised UARL for a system, zone or DMA. How FAVAD, pipe materials and pressure burst frequency relationships may influence the standard UARL calculation. In the first part of this presentation, I'll outline the evolution of UARL since 1995 and the assumptions that were used to summarise the multiple influences on leakage into the relatively simple linear standard equation for UARL, which is now used in many countries worldwide as the basis for calculating how low could you go with leakage, and the calculation of the infrastructure leakage index. When introduced in 1999, lower limits for system size and pressure were set for use for the UARL equation. I'll then show some ILIs less than 1 which have been reported by large utilities in 2 of the best performing countries at relatively low pressures, and also some low ILIs in small systems less than 5,000 service connections. We'll then explain the 3 additional factors which have been used collectively to customise any individual UARL calculation using a system correction factor, SCF, which varies with pressure. The key takeaways will then be summarised. I'll then show some examples of UARL with SCF calculations, which demonstrate how pipe materials, system size and pressure can be key influences not only on the UARL in small systems at lower pressures, but also in all systems at higher pressures. The UARL equation and ILI were developed by the first IWA water loss task force, using the foundation concepts of component analysis of leakage, bursts and background estimates, and fixed and variable area discharges, FAVAD. 27 diverse systems in 20 countries were used to test the methodology. UARL predicts how low could you go with leakage in whole systems with diverse characteristics of mains length, number of services, meter location on service connection and pressure. Originally limited to systems with more than 5,000 service connections, UARL assumes a simple linear relationship between pressure and leak flow rate. Relationships between pressure and burst frequencies did not exist in 1999, so fixed burst frequencies based on international data standardised for 50 metres pressure were used, whatever the pressure. This is the metric version of the UARL equation in cubic metres per day, which uses 3 infrastructure size parameters: mains length, LM, number of service connections to property line, NS, and total length of underground private service connections, LP, if the meter is located some distance after the property line. Leak flow rate is assumed to change linearly with pressure. Some of you will know this as N1 equals 1.0. Burst frequency is fixed, whatever the pressure. The coefficients 18, 0.8 and 25 are derived from auditable assumptions for burst frequencies, average flow rates, durations and percentages of unreported and reported bursts. This slide is credited to Roland Limburger and several water loss specialist group members. Our thanks to all of them. This slide is based on an original idea by David Pearson. It shows how the 4 components of leakage management are used to squeeze the current annual real losses, CARL, derived from a water balance, shown as a grey box, to try to achieve unavoidable annual real losses, UARL, which is the yellow box. The infrastructure leakage index, ILI, equals CARL divided by UARL, and this diagram represents an ILI of around 4. This slide shows sets of ILI data from 12 countries and is available on the Leak Suite Library website. As calculations of CARL and UARL both involve some uncertainties, ILIs are usually quoted to just 1 decimal place. Netherlands and Danish utilities with relatively low medium pressures, 32 and 34 metres, have been able to achieve median ILI values less than 1.0. Sample data from Aqua Flanders, Germany and Austria had median ILIs of 1.0 at 39 to 50 metres pressure, and Australia achieved a median ILI of 1.1 in the Millennium Drought. The standard UARL equation has proved a robust calculation for large utility systems at around 40 to 60 metres pressure. Other countries' median ILIs are in the range 1.7 to 4.5 at 40 to 51 metres pressure, indicating scope for further improvements if utilities consider it to be economic to do so or necessary for water conservation. These graphs show ILIs for individual Netherlands and Danish utilities as blue columns, related to performance categories A to D, very low, less than 1.5, to very high, more than 8, on the left side vertical axis. Average pressures are shown as dots related to the right-hand vertical axis, with pressure categories from very low, less than 30 metres, to very high, more than 80 metres. Utilities in Netherlands and Denmark operate at 25 to 40 metres pressure, and most have achieved ILIs of less than 1. Netherlands data is for utilities with 200,000 to 2.6 million service connections. The Danish range is 4,000 to 50,000 connections. This large system data showed that further understanding of relationships between UARL and pressure was needed to take account of the sensitivity of different pipe materials, rigid or flexible, to pressure leak flow relationships, FAVAD and M1, and pressure relationships, which were not known or included in the original UARL equation. Some countries have a few large systems and numerous small systems. In Austria, 90% of systems have less than 3,000 connections. This high-quality data set for systems with 240 to 10,000 service connections, kindly provided for analysis by OVGW, has median pressure of 50 metres. As system size falls below 5,000 service connections, there is a greater scatter in the ILIs and a steep reduction in minimum ILIs as system size reduces below 3,000 services. This small system data confirmed that further understanding of relationships between UARL and small system size was needed. As the UARL and ILI concept became increasingly popular, many leakage practitioners wished to use it for analysis of leakage in smaller systems, including zones within larger utilities, DMAs and small standalone systems. Some of you may have seen this table, which summarises attempts to reduce the lower limits for use of the UARL equation to meet this demand, but it could not meet the need to extend UARL to all small systems and DMAs. A 2020 update will be shown in a later slide. Let's look at research carried out since 1999. In 2009, it was clear that the simplified linear pressure leak flow rate relationship could over-predict UARL for systems with low pressures and high percentages of flexible pipes. By 2014, we already knew that in a few systems where all leak surface, UARL equation was around 20% too high. Uncertainty analysis had also shown that at ILIs close to 1.0, uncertainty of CARL calculations from water balances could be plus or minus 20%. Also in systems with less than 1,000 service connections with continuous night flow measurements, an unreported burst can be easily identified and repaired faster than allowed for in the UARL equation. But the Austrian data shows that these explanations can't explain all low ILIs, and including mains length in the lower size limits doesn't solve the small systems problem. In 2019, Allan Lambert decided to look at an approach based on optional customising of the UARL equation using a system correction factor, SCF, which includes the interaction between 3 additional factors for each individual system. So how can an SCF for the UARL equation be customised? Option 1, FAVAD only, the pressure leak flow rate relationship. Includes the influence of pipe materials, fixed and variable area discharges, on pressure leak flow rates relationships. Unavoidable background leakage, which makes up around 60% of UARL, behaves as a variable area discharge sensitive to pressure, N1 equals 1.5. Option 2, Poisson and FAVAD. Adopt a more appropriate statistical approach, the Poisson distribution, for low burst numbers in small systems. Use median, 50% exceedance probability, as more representative than the average UARL burst frequencies. And option 3, pressure burst relationship plus Poisson plus FAVAD. Include the influence of a general international relationship between pressure and burst frequency, not available prior to 2013. Many of you will be familiar with the FAVAD concept, proposed by John May in 1994 and now widely used internationally. His insights into pressure leak flow rates and pressure bursts stimulated Allan's passion for this subject 25 years ago, and he set the paths that Allan has tried to follow. For a fixed area burst, such as a ring crack in a rigid pipe material or a corrosion hole or blowout, the leak velocity varies with the square root of pressure. The leak area is fixed, so the leak flow rate varies with the square root of pressure. The green curve shows these flow rates are relatively insensitive to pressure, using power law N1 equals 0.5. For a variable area burst in a flexible pipe material, the area varies linearly with the pressure, and so the leak flow rate is much more sensitive to pressure, which is the blue rising curve. Background leakage at joints and fittings, which account for around 60% of UARL, also acts as variable area leakage, N1 equals 1.5. When fixed area and variable area leakage are added together, the brown curve, the result may be similar to a straight line, N1 equals 1, for large systems with higher proportions of rigid pipe materials, which is why the 1999 UARL equation assumes a simplified linear relationship between average pressure and leak flow rate. This graph from 2009 shows how a pressure correction factor, PCF, for the 1999 UARL equation could vary for a system with 100% rigid pipes. The pressure correction factor stays within 0.9 to 1.1 from 8 to 75 metres pressure. However, for 0% rigid pipes, which is 100% flexible, the leak flow rates are much more sensitive to pressure. The PCF is only within 0.9 to 1.1 for 40 to 60 metres pressure. It is much lower than 0.9 at low pressures and higher than 1.1 at high pressures, and these graphs make no allowance for the influence of pressure on burst frequencies. Here we can see the assumptions used to calculate coefficients in the 1999 UARL equation for unavoidable background leakage, average burst frequencies, and percentages of reported bursts on mains, service connections to property line, and underground services from property line to meter, if the meter is located at a distance from the property line. The assumptions for average burst flow rates and runtimes are clearly stated and auditable in the 1999 Aqua paper, where the UARL equation was first published. The Poisson probability distribution is used for predicting the probability of occurrence of a number of isolated events in an interval of time when only the average number is known. It can be applied to the analysis of low annual UARL burst numbers in small systems. This graph shows the Poisson probability distribution of 0, 1, 2 or 3, etc. UARL bursts when the annual average number of bursts per year is known from the UARL assumptions. At an average of 15 UARL service bursts per year, equivalent to 5,000 service connections at 3 per 1,000 connections per year, the shape of the distribution is close to a normal bell-shaped distribution. As system size decreases and the distribution becomes skewed, the chance of getting less than the average number of bursts exceeds the chance of getting more than the average number of bursts. For example, if you have a DMA with 1,000 service connections, you have a 42% chance of getting less than 3 bursts, but a 36% chance of getting more than 3 bursts. The median number of bursts, which is exceeded in 50% of years, becomes a better measure of the probability of bursts in any single year, and the median of a positively skewed distribution is less than the average. In 1999, there was very little conclusive evidence of any relationship between static pressure and burst frequency, and most practitioners were sceptical. With colleagues from the Pressure Management Group of the 2nd Water Loss Task Force, led by Julian Thornton, this began to be investigated in 2003. The first output was the simple straw that breaks the camel's back concept in 2006. Allan used good quality before and after data in large pressure-managed zones during the Australian Millennium Drought from 2000 to 2011 to develop the latest generic form of a relationship published in 2013. This has since been tested and used successfully in Australia, South Africa, UK and other countries. It contains a non-pressure dependent component, BFNPD, and a pressure-dependent component, BFPD, that varies with the maximum average zone pressure, AZP max, to the power 3. Each component of infrastructure, mains, service connections from the main to the property line, and service connections after the property line, has BFMPD parameters based on data from high-income countries with ILIs in the range 1 to 1.5. At 50 metres pressure, the curve passes through the UARL burst frequency used in the original 1999 equation. Burst frequency rises slowly between 20 and 50 metres, then begins to rise rapidly at pressures exceeding 50 metres. So here is a summary of where this research has reached. There is now an optional methodology to predict a system correction factor to customise the UARL equation for any individual system, zone or DMA. Optional checks to see if the UARL equation is likely to be over or under predicting UARL by plus or minus 10% are likely to be relevant for small systems with less than 5,000 service connections and or systems outside the average pressure range of 45 to 60 metres. The right-hand table shows that 4 parameters are required for the standard UARL equation, with an additional 3 parameters for FAVAD only, FAVAD plus Poisson, and FAVAD plus Poisson plus pressure bursts. The other assumptions for each of the 4 options are also summarised. So key takeaways from the UARL with SCF research are: it progresses our understanding of how low could you go by including more key factors in individual systems of any size. It replaces the lower limits for application of the UARL equation. It identifies systems at lower pressures where current targets based on standard UARL may be too high and lower leakage could be achievable. It identifies systems at higher pressures where current targets based on standard UARL may be too low and may need to be increased. And it demonstrates how reductions of excess pressure can reduce both UARL leakage and median burst frequencies. WLRNA's challenge in this research process was to take Allan's interlinking concepts and equations and produce online software which could quickly calculate system correction factor and UARL at current average zone pressure and at any average pressure between 10 and 100 metres, and show the results in a simple, user-friendly format on a single screen. The equation on screen shows how the system correction factor is used as a coefficient to individually customise the standard UARL equation for each system, zone or DMA, taking into account the combinations of additional factors shown in red in the white boxes at the bottom of the screen. These are N1 values of 0.5 or 1.5 for pipe materials, assessed from the percentages of rigid and flexible pipe materials, the median rather than average burst frequencies using the Poisson distribution, which influences small systems, and the pressure burst relationships for each infrastructure component. Let's look at a couple of example calculations of UARL with SCF, but first I want to show you how simple it is to perform a calculation with a maximum of 7 items of data needed for a whole system, zone or DMA. Then we'll look at calculations for 2 sizes of system, 5,000 service connections and 1,000 service connections, both operating at a relatively low pressure. Finally, I'll summarise the range of calculations that WLRNA has performed to date. The input section has space at the top to track the date of the calculation, the utility and system name, along with a comments section to record any other useful system or zone information. The 4 inputs for system data are the usual figures required for a standard UARL calculation. The number of service connections, mains to property line or curb stop, the average length of service connections from the property line to the meter, mains length and average zone pressure. The 3 additional inputs are for the percentages of rigid pipe materials on the 3 components of infrastructure. Help options are available for both of these items. All calculations are stored online, so can be retrieved at any time and downloaded or printed in PDF format if needed. So our first example is a system at 35 metres average pressure with 5,000 service connections with 20% rigid pipes. Customer meters are located an average of 10 metres after the property line with 50% rigid pipes, and there are 125 kilometres of mains with 80% rigid pipes. When you perform a calculation, you'll see the results laid out as you can see on screen. There are 5 main areas to explain here, highlighted in red boxes. First, in the top left-hand side of the screen, you can see the input section, which you're already familiar with. The rest of the screen shows different results data for the calculation, starting with the bottom left-hand side of the screen where you can see the pink results section. This shows the numeric values for the system correction factor, taking into account just FAVAD, FAVAD and Poisson, and FAVAD, Poisson and pressure bursts. Below this you will see the values in cubic meters per day for the standard UARL calculation, using the original equation, then the values for UARL corrected with a system correction factor for just FAVAD, FAVAD and Poisson, and FAVAD, Poisson and pressure bursts. At the top of the screen you will see a bar chart which displays the median values for annual UARL bursts across mains and services, again considering just FAVAD, FAVAD and Poisson, and FAVAD, Poisson and pressure bursts. The first graph plots the values for system correction factor against average pressure, and the table below gives the numeric values which are used to generate the graph. The second graph plots UARL with system correction factor and unavoidable background leakage against pressure, with the table of numeric data showing beneath it. Each distribution system, zone or DMA will have its own signature characteristic curves for system correction factor versus average pressure, and for UARL in volume per day versus average pressure. Let's drill down into some of the areas of this calculation. First, let's look at the results section, which shows that in this system at 35 metres pressure and for 5,000 service connections, there are real differences between the standard calculation for UARL and those values corrected for FAVAD, FAVAD and Poisson, and FAVAD, Poisson and pressure bursts. You can see a small adjustment when considering the effects of FAVAD with a system correction factor of 0.90. A further small adjustment when considering the Poisson effect. This is not a very small system after all. But when we consider the pressure bursts as well, it gives us a value for the system correction factor of 0.76. So depending on which influences you consider, the UARL could be between 10 to 24% or 27 to 63 cubic meters per day lower than predicted by the standard UARL. For this particular calculation, on screen you will also see the values for litres per connection per day for standard UARL and UARL corrected for FAVAD, FAVAD and Poisson, FAVAD, Poisson and pressure bursts. This bar chart shows the predicted median number of UARL bursts across mains and services. Again, you can see a small reduction in bursts when the Poisson effect is considered, from 38 down to 34 bursts in total. But because this system is operating at lower than 50 metres average pressure, when the pressure burst relationship is also considered, we see the median bursts reduce further to 28 in total. This graph shows the relationship between the system correction factor and average pressure for the standard UARL calculation, as well as for FAVAD, the green line, FAVAD and Poisson, the purple line, and FAVAD, Poisson and pressure bursts, the red line. The grey horizontal line on this graph represents the standard UARL, which has an SCF of 1. Take a look at the green, purple and red lines at 35 metres average pressure, which is the vertical dotted blue line on the graph. UARL is overestimated regardless of which of these effects are taken into account. And if pressure is increased, notice how the green, purple and red lines change. If we look first at the green line, which is system correction factor for FAVAD only, the line shows that it's the least sensitive to changes in pressure, as we've got a relatively high proportion of rigid pipes. That green line is within plus or minus 10% of an SCF of 1 for pressures in the 35 to 65 metre range. If we look at the purple line, which is SCF considering FAVAD and Poisson, we see a further reduction when the Poisson effect is included, and the purple line is within plus or minus 10% of an SCF of 1 for pressures in the 47 to 80 metre range. Finally, if we look at the red line, this is for the system correction factor, including pressure bursts, Poisson and FAVAD effects. When pressure bursts are included, we see a further reduction in the system correction factor at 35 metres. but the system correction factor rises above 1 when the pressure exceeds 56 metres. And the red line is within plus or minus 10% of an SCF of 1 for pressures only between 48 to 64 metres. Overall, what we can see is the importance of controlling average pressure, and for this specific system, there is a very narrow range of operating pressures from between 48 to 64 metres, where the UARL, when we consider pressure bursts, Poisson and Favard effects, is within plus or minus 10% of the standard UARL equation. This graph and table show standard UARL, UARL with SCF for Favard, Favard and Poisson, and Favard, Poisson and pressure bursts, as well as unavoidable background leakage. The unavoidable background leakage component in the standard UARL equation was, for simplicity, assumed to vary linearly with an N1 equal to 1 with pressure, which is shown by the dark blue line on this graph. But it actually behaves as variable area leakage, with an N1 equal to 1.5, represented by the light blue line on the graph. As several of the lines and curves are close together at low pressures, it's recommended to use both the graph and the table below it to interpret the data. This graph and table are very insightful, as they allow an approximate estimate of the relationship between average pressure and UARL with SCF to be derived from the slope of the lines for any value of current average pressure. For example, 8 cubic metres per day per metre of pressure for Favard plus Poisson plus pressure bursts at 35 metres pressure. Our second example is a system which is 1/5 of the size of the first example, still operating at 35 metres average pressure, but now with 1,000 service connections, 20% rigid pipes, customer meters located an average of 10 metres after the property line with 50% rigid pipes, and 25 kilometres of mains with 80% rigid pipes. Let's see how the calculations change for this small system. This slide takes the system correction factor versus average pressure graph from example 1 and example 2 and compares them side by side. Note that the green lines, which are SCF and Favard, in both graphs have the same shaped curves and the same values for system correction factor. Comparison of the purple curves, which is Favard and Poisson, shows how the Poisson effect has a bigger influence as system size decreases below 5,000 service connections. The system correction factor reduces from 0.9 to 0.81 for the larger system, but from 0.9 to 0.67 for the smaller system. Comparison of the red curve in both graphs for Favard, Poisson and pressure bursts shows further reductions of system correction factor at pressures less than 50 metres. So at 35 metres from 0.81 to 0.76 for the larger system and 0.67 to 0.64 for the smaller system. It also shows larger increases in the system correction factor at pressures more than 50 metres. For example, at 70 metres, 0.76 to 1.18 for the larger system and 0.64 to 0.99 for the smaller system. Finally, let's compare the annual median UARL burst frequencies for each of these examples. In example 2, in the lower part of the screen, our small system, UARL bursts will be relatively rare events, and this is reflected in the lower bar chart values of 7.6 annual bursts, just considering Favard across mains and services, to 3.3 annual bursts across mains and services when considering the Poisson and pressure bursts effects as well. Over the last year, WLRNA has performed a range of UARL calculations with SCF in Australia, Austria, Belgium, Canada, Malta, Netherlands, UK and USA. These calculations have been performed for DMAs and whole systems, so anything from 120 to over 1 million services, with a density of connections between 10 to 65 per kilometre, service length from the property line to the metre of 0 to 26 metres per connection, and all ranges of mains materials 0 to 100% rigid and services materials 0 to 100% rigid, with average pressures of between 25 to 100 metres. So in summary, System correction factor allows UARL to be applied to small systems, zones and DMAs. And the diagnostic approach may also be useful for some larger systems. It enhances but does not replace the standard UARL equation. You can find out more about the research at the Leak Suite library. UARL with SCF software is available online in metric and US units, and one rapid UARL calculation per DMA, zone or system should be valid for several years unless infrastructure changes significantly. You can find out more information on UARL with SCF, including software simulations and datasheets, at wlrna.com/software.